Hi, welcome to the presentation. I'm Tianshi Yu from the Human Robotics Lab, the University of Melbourne. In this work, the active transhumeral prostheses for the above elbow amputees are studied. Specifically, what we investigate is the prosthetic interfaces that are characterized by the input features and regulate the prosthetic elbow joint movement. The input features here are the common variables which are processed from the residual limb movement, for example, the shoulder adduction-abduction movement, and the muscle activities, for instance, the root mean square value of biceps surface EMG signal. In this paper, we attempt to use a surrogate measure, the separability, to evaluate the input features performance in classifying the user-intended target poses. And the evaluation is done during the stage of designing the input feature set before implementing the interfaces. Let's start with the background. In active prostheses, conventionally the joints are controlled through surface EMG interfaces, which usually lead to a sequential movement. The user needs to move the residual limb first, and then command the prosthetic joints by contracting muscles, which can be cumbersome to use. Coordinated movement, which is natural and efficient in completing tasks, is thus preferred, where we see the prosthetic joints move with the residual limb movement. To achieve coordinated movement, kinematic and surface EMG input features were utilized in the literature. However, most work select any input feature set by design observational or trial-and-error methods. Then the interfaces are implemented using the selected input feature set, and the performance is investigated and reported. Further optimizing the design of the interfaces requires being able to iterate based on the performance conveniently. Therefore, the question is how to do so without having to test the input feature set on human experiments. In this paper, we attempt to use a surrogate measure to evaluate the input feature set before implementing the interfaces. The surrogate measure should correlate the performance of the input feature set, which is also called as the information content here, and the proposed surrogate measure here is the separability. The idea of the measure is to evaluate how well the different poses can be distinguished based on the selected input feature set. For example, the case of using two input features, feature 1 and feature 2, to distinguish three target poses which have different elbow poses here but the same shoulder pose. The shoulder flexion extension is mostly used in the recent work as the input feature to achieve coordinated movements, as we see in this video. However, the elbow poses can be at the same shoulder pose, and thus shoulder flexion extension would be a poor indicator for the human intention. This further highlights the importance of evaluating the information content of the input feature sets at the design stage. Okay, back to the main problem. In order to know how effective the input feature set is, we use the following intuition. The ideal input feature set should have small intra-class distance and large inter-class distance. Following this, we adopt a surrogate measure. We use scatter matrix-based separability measure. It scores high with an average small intra-class distance and an average large inter-class distance. The S measures the trace of SW inverse times SB, where SW is the intra-class scatter matrix and SB is the inter-class scatter matrix. We will refer to S to separability in the following talk. The detailed definition of S can be found in the paper. And so, at this point, the definition of separability is shown. We hypothesize it's a good measure for the performance in identifying which pose is intended by the user from the selected input feature set. To test the hypothesis, we conduct human experiments in virtual reality environments with 10 able-bodied subjects. The subjects perform different target poses as shown on the left side, which demonstrates the side view of the upper limb. 9 discrete upper limb poses, denoted as T1 to T9, are designed, where we have different elbow poses at the same shoulder pose. The targets, which are orange circles, are the fingertip positions and set in the parallel sagittal plane of the subject. They are displayed as a sphere in a VR environment, During the experiments, the subjects were asked to use the virtual hand, which is controlled by the controller in the subject's hand, to reach the target and hold for 1 second in order to allow the quasi-static data upon reaching to be collected. The information we collected from the experiments are a wide range of input features upon the user reaching the intended target pose. For the data collection, upper arm and upper body kinematic movement were captured by the HTC Vive trackers, which are embedded with inertial measurement units and motion capture sensors. Delta's surface EMG sensors were attached to the subject's upper arm muscles. Based on the collected data, 34 features were extracted and categorized. 6 of them were kinematic-based, including shoulder, scapular, and trunk movement. For instance, shoulder rotational movement contains shoulder flexion extension and adduction abduction. 28 of them were SEMG-based features. We used 7 SEMG electrodes. For each electrode, 4 time domain features were extracted, which includes mean absolute value, wavelength, zero crossing, and slope time change. Then we test the hypothesis based on data. We selected 2 input features from the 34. The chosen 2 are with the highest separability measure for the 9 target poses, or we say the classes. We only discuss the top 2 features to keep a low complexity. First, here on the left side, we measure the separability of every target pose pair and sort it into a symmetric matrix. Each entry is the separability for 2 target poses. For example, the separability of class 1 and 2 is the entry with red circle. Pose class 1 and 3 is the entry with blue circle. Class 2 and 3 is the green circled entry. The lighter the color, the higher the separability. The blue circle has the highest separability among the 3. This is symmetric to diagonal. The separability of class 1 and 2 is the same as class 2 and 1. The diagonal entries are separability for 2 same classes, so the values are 0. On the right side is the classification accuracy, which is sorted in a confusion matrix. The scale is 0 to 1 to align with the separability measure. Linear discriminant analysis classifiers are trained to obtain the resulting accuracy. The vertical axis is the true class number, and the horizontal one represents the predicted class number. Here we can observe a high correlation between the separability and the classification accuracy. For example, target pose 1 and 3, the blue entry, have the highest separability and the lowest rate of misclassifying between them. The red and green entry have lower separability comparing to the blue one, and the misclassification rate is higher than the blue entry. Next, we quantitatively compare the top 2 features from 3 modality cases. First, KE, kinematic plus SEMG. Second, K, kinematic only. And third, E, SEMG only. The kinematic plus SEMG KE has the highest accuracy in classifying the target poses, also the highest minimum pairwise separability. For the main pairwise separability, the KE is slightly lower than kinematic only case K, but no significant difference is detected. This is caused by some highly uneven class distributions, where the main pairwise separability can be affected, such as in the scenario shown in the figure. And the minimum pairwise separability can be a useful metric for future systematic input feature selection algorithm. From the above results, we can see the KE case with higher separability have higher accuracy in classifying the user intended target pose. Finally, to conclude the talk, in this work we show, through human experiments, the adopted serogram measure separability correlates to the performance, which is the accuracy of identifying the user intended target pose. The evaluation is done at the input feature design stage before implementing the interface. Moreover, kinematic plus SEMG provides a richer set of information and thus higher separability and accuracy. For future work, the algorithm to systematically select the input feature set can be developed based on the serogram measure. You are welcome to email us if you have further questions, and here is the contact information.